Chapter 16, Chemical Equilibrium. Up to this point, we've been assuming a reaction, such as the generic one stated here, will proceed to completion, meaning only products C and D will remain when we've run out of reactants A and B. In Chemistry 20, we even talked about limiting reactants, where the amount of a product produced is dependent upon the least available reactant. If we react A with a limited amount of B, when the reaction is over, we will have products C and D and some unreacted reactant A. However, in reality, many reactions do not proceed to completion. What actually happens is the rate of the reaction going the other way catches up to the forward reaction rate. And at the point where they are the same, no net change in reaction is indicated. We write a normal reaction like this. The single arrow between the reactants and products indicate a quantitative reaction. We say the forward reaction if we're looking at it from left to right. The arrow going the other way indicates the reverse reaction. While some reactions don't have a reverse reaction, like hydrocarbon combustion reactions for example, many in fact do, and are indicated with a double arrow. Now the double arrow used in your book will not look like the double arrows I use on these slides. It doesn't really matter, as long as it's clear it's a double arrow. Initially, when reactants are added to a reaction vessel, the forward reaction rate is greater than the reverse because the concentration of the reactants is very high compared with the concentration of the products. But as the concentration of the products increase, the rate of the reverse reaction increases. It gets to a point where the rate at which the reactants combine to form products becomes equal to the rate at which the products combine to reform the reactants. At this point, the reaction is said to be in equilibrium. So equilibrium then is the rate of the forward reaction is equal to the rate of the reverse reaction. Another way to express this is to say that at equilibrium the concentration of the reactants and the products remain unchanged. This is not to say that the concentrations of the reactants and products are the same. At equilibrium, we have constant macroscopic properties. This means observable properties like temperature, color, and pH do not change when a system is at equilibrium. However, because of the continuing motions of particles, products are realigning to become reactants, while at the same time reactants are being turned into products. So the chemical system at equilibrium is not a static thing, it's dynamic. Both physical and chemical changes can reach equilibrium. A physical equilibrium example would be sugar crystals added to a saturated sugar solution. In this physical equilibrium system, the added sugar dissolved in the solution, and since the solution is saturated, dissolved sugar crystallizes. In your introduction to solution chemistry in Chemistry 20, you already learned this type of equilibrium. There are two types of chemical equilibrium processes. The first is homogeneous equilibrium, where reactants and products are in the same phase. This is the type of process we will focus on in this unit. And heterogeneous equilibrium. Reactants and products are in different phases. Whether physical or chemical, there are four conditions that apply to all equilibrium systems. The first is the rate of the forward reaction is equal to the rate of the reverse reaction. As already mentioned, the system at equilibrium has to involve a reversible process. Remember, not all processes are reversible. A chemical system in equilibrium is indicated by the double arrow in the chemical equation. No change at the macroscopic level. That is, no observable changes like pH, color, temperature, pressure, and so on. It must be in a closed system. An isolated system is better but difficult to achieve. The important thing is that no change in matter or change in energy be applied to the system at equilibrium. An equilibrium can be approached in either direction. Take a chemical system in equilibrium, I could write the reaction like this, where A and B react to form products C and D. Or this, which is equally as correct. C and D react to form products A and B. The two equations are, of course, different, and we shall soon see it is very important to recognize that the concentration of products when C and D are products are different than the concentration of the A and B products.